Hey, hello everybody. Before we get started, I'll just remind everybody of the Zoom etiquette. So throughout the seminar, all audience participants will be muted. Please don't attempt to turn on your video or share your screen during the talk. At the end of the talk, there will be an opportunity for you to ask questions, just like a normal seminar. Once the talk is over, you can use Zoom's raise hand feature to notify the meeting host that you'd like to ask a question. You can also put the questions in the chat if you wish. The raise hand feature is located just under the reactions tab at the bottom of the Zoom window. Okay, so it's my pleasure to introduce our seminar speaker for today. Jonathan Warrick is a research geologist at USGS in Santa Cruz. He started out in the CSU system and in Cal Poly, moved out to Wisconsin for his master's, and then missed the ocean so much that he came back to California to get his PhD at UC Santa Barbara and has been at USGS ever since. His research focuses on the intersection of rivers and the sea. This includes movement of sediment from coastal watersheds and how sediment alters the coastal landscape. Last time he spoke at MLML, he was talking about the effects of the Elwha River dam removal. And today he'll be talking about a topic that's close to our backyard. His talk is Fire plus Flood equals Beach, Observations of Coastal Change in Big Sur, California. I'll let you take it away, John.
Great, thanks, Tom. I'm assuming you can hear me. So let's check on that first before I get going.
Yes, we can hear you.
Okay, great, thanks. Well, before the seminar, we were talking quickly, and I was thinking about how much fun it was to come down there and talk about the Elwha, and how wonderful it was to talk to students afterward. And so I'm going to make myself available at the end of this talk. If you have any questions, thoughts, you have ideas about your own research, or something in this was interesting to you, I'd like to be here for you. Interacting with students is one of the best parts of the job, and so I'll make myself available. And if you're not available, you can certainly email me if any of this is interesting or is maybe related to some of your own work. I want to point out that I did this work with a couple co-authors. You'll see their names there. Killian Voss from the University of New South Wales, Amy East, who's a colleague at the USGS, as is Sean Vatusek. And I'll try to point out their contributions as we go. By all means, this was a multi-authored entity, and they contributed significantly to this. So I'm hoping that I'll make sure to point out some of their contributions as we go. So if we think, kind of on the big picture, kind of our coasts are facing several challenges, and I know you're probably learning a lot about this in your coursework and in your research. And one of the things that we've been very interested in studying is sea level rise, and this comes from the most recent IPCC report that just came out. And in there, if you look at these numbers, you'll see that the rate of sea level rise has increased about 3 times or so during the 20th and early 21st century, and that human influence is very likely the main driver of that. And so we may ask the question, how will that sea level rise influence the coast? And so for some hints on this, you can go to the IPCC special report on the oceans. And there's some nice materials in there. Of course, there's a lot of good research on this too. And basically the risks for erosion and flooding, and for saltwater to enter our aquifers and other hydrologic systems, are expected to increase with time, of course. And there's very high confidence in that. I've underlined that in this slide. And so you may ask, what will happen to our coastal landforms, and can they persist through these changes? And again, this is covered in the IPCC report, and the paragraph here, I've underlined a sentence where they talk about these landforms, the salt marshes, mangroves, etc., that they can build vertically and that they can expand laterally in response to sea level rise, although this capacity varies across sites. And so generally when I think of building vertically and expanding laterally, there's sort of two different ideas there. One, the building vertically, sorry about my dog, would be the addition of sediment. And so a landform can build vertically if sediment is added to it. And it can expand laterally, of course, if there is sort of geography to do so, if there is the space laterally to do so. And some systems have that and some systems don't. Of course, these things vary quite a bit. Sediment availability and sort of the geography of coastal landscapes varies tremendously around the world. And so that's why there's that sort of caveat at the end of this sentence. So we can take this to our backyard here in California and think about how can you apply that to California, and what will be the future of California's coastal landscapes. And I would suggest that the future of the California coast will be related largely to sediment, and that's because of a few things. One, we have a system that's sort of sediment dependent already. We sit on this active margin where sediment is readily supplied by rivers and by cliff failure. And we have this littoral and coastal system that sort of is derived by that sediment. And sediment is fed through it over scales of decades and centuries and maybe millennia. And that's sort of shown in this image here on the left, and sediment coming through and running down the coast and then falling down canyons. And so and also we have a fairly narrow coastline, much of it is built on. And so we have sort of a narrow area to expand laterally. And so sediment's going to be a big player in where our coast will be in the future. And of course, sediment can come from various sources, from rivers, which is probably the dominant source for much of the California coast. Of course, bluffs and cliffs provide a very significant source. And there's been a lot of work into thinking about, can sediment be added to this system from various places, whether it's offshore sediment or inshore, et cetera. And these are really important topics to sort of understand, to figure out where the coast may be in the future. And to show sort of some of the importance of river-derived sand on our coast, this is just, I made this is an oblique perspective of the Santa Clara River mouth, which is down in Southern California, showing the 2005 floods and the effect of the new sediment that came out to the coast following that year. If you're interested in this topic, Patrick Bernard and I wrote a paper on actually this event. We have a lot of topographic measurements and bathymetric measurements from this, but I thought it'd be interesting just to show sort of the Google perspective, Google Earth perspective of this. And you can see that sediment pushing way out to sea. And then if you look sort of down coast, you can see how the shoreline expands down there. You can't see it anymore, but you could have seen during that video how the shoreline expands laterally. And what's really neat is if you look over longer intervals of time and hear from a technology that I'll be focusing a lot on today, which is the COSAT system that used Landsat and Sentinel-2 imagery, you can see that the shoreline goes through intervals of these or cycles of this sort of supply and then redistribution of that supply. And so this is for a transect right along the Santa Clara River mouth. And so this is the shoreline position derived from those satellite data. I'll talk about this in a second, how this is derived. But you can see this sort of sawtooth pattern. And these big sort of widening of the beach here, those are related to those really, really wet years where we had a lot of discharge from the river and an active supply of sand coming from the watershed and resupplying the beach. And so these are really important sort of events to understand, to understand how the beach is evolving over time. So looking forward, there's a lot of folks who are trying to think about what we may be seeing in our watersheds with climate change. And this comes from a colleague, Joel Sankey and others, who have looked at this. A lot of this is modeling work in trying to understand in the West here, our watersheds most likely will be shedding more sediment over time from the combination of climate and wildfire. And in general, we expect that wildfire intensity and size and incidents will be increasing, whereas climate will probably get warmer, have prolonged droughts, but when we get precipitation, we'll probably get a lot more intense precipitation. And the combination of those two things will most likely mean more sediment coming down our watersheds. Now, this will probably vary with time and with space, but sort of on a big picture scale, this is what we're beginning to think may happen. And one example of this could be seen last year. Obviously, last fire year was quite a big fire year here in the West. These images from the San Francisco Chronicle provide distribution maps of the wildfire season last summer, and then this January storm. And I want to focus in on the Big Sur region, where we had a fairly large wildfire last summer. And then in January, we saw an atmospheric river come through and deliver well over a foot of rain to the coast. And of course, if you remember, Highway 1 failed, and there were a number of debris flows occurring up and down the coast. So one of the things that we do in the USGS is we fly along the coast and take oblique photos. And some of the photos before, or one of the photos before and one of the photos after that January event is shown here. And this is Mill Creek in Big Sur. This is not where the highway failed, but this is it's another one of the creeks that had a major debris flow come down it. And it was so big, it actually destroyed this house and many of the buildings on it. You can see just boulders and logs that made it all the way to the beach. And there was well over a meter of deposition. So this image here, this little GIF here, is a comparison. It's an oblique comparison of the structure from motion photogrammetry point cloud we derive from our photos. And you can see the beach popping up there. And so this is the type of event that can occur following wildfire and heavy precipitation. These data are still sort of a work in progress, and we've collected some more imagery this summer, and we'll continue to track this over time in the coming years. But this just sort of is a more current event showing the same kind of thing. So today I want to focus on two research questions. The first is how do wildfire and coastal flooding and flooding events in the watersheds influence coastal shoreline positions? And the second question, and that's sort of just to help us fill the gap in our understanding for sediment loading to the coast. It's although wildfire and flood, wildfires followed by floods are somewhat rare, they seem to produce a lot of sediment, and they may be a dominant source of sediment supply to the coast. So we want to understand these events better. And the second question is can we use satellite imagery, some of which I showed just a second ago, to better understand these coastal processes? And the reason we're interested in that is because if they can, then that really opens the door to a lot more analysis that could be done from these imagery. As I'll show you in a second, there's a tremendous amount of imagery available. And if these are useful to tracking our beaches and our coastal systems, then we have sort of a new tool in our toolbox to be able to investigate these systems better. And so today we'll focus on the Big Sur River. And the Big Sur River is obviously right there in the middle of Big Sur. You probably know as you drive along Highway 1, you sort of parallel the Big Sur River. There's a number of campgrounds here. And you actually are only in the Big Sur watershed on Highway 1 for a while. And then sort of at Nepenthe, you cross back over and come back on the coast. The Big Sur watershed is this blue line. It goes way back inland to these peaks that are almost 1,500 meters high. So very steep, rugged landscape back there. And one of the reasons we are interested in this watershed is because in 2016, the Soberanus wildfire burned about 2/3 of this watershed. You can see it's mostly in the upper watershed. The lower watershed wasn't burned, but this really steep region was burned extensively. Let's focus in on the coast here really quickly and look at that. This will be sort of our study area. The Big Sur River comes in here on the northern section right behind this point, and there's this this narrow sand and rock beach that is sort of hard to pass at high tide, but there is the little pockets of sand along it. And there's a small little headland down here on the south, about 2 kilometers south of the Big Sur River. And so we're going to just focus on this area for most of the talk today. And here is what it looks like. I'll go back really quick. If you stand sort of right in this area, a little over 1/2 kilometer away from the river mouth, and look back up the coast, the river mouth is sort of tucked behind the bluff there. And then you look down coast and you can see the coast here. One of the things I want to point out is that there are these rocky areas in the coast, one of which is sort of standing on here, and there's a few more down the coast. And note that the shoreline is sort of somewhat curved between these. It's cuspate-ish, and I'll touch upon this a little bit in the talk, how these rocky areas sort of stick out a little bit more in terms of the shoreline position. You can see both the sand and the waves sort of follow that curvy nature. And if you look back at the satellite image, you can sort of see this. There's one of those and 2 of those, 3, and then there's this little headland. So I'll focus a little bit on that during my talk. I just wanted to point that out as before we get into a lot of the data. As you know, this is a really strongly seasonal place, both in its hydrology and, of course, in its in the waves that come. Waves are dominated by winter waves, where waves that come from the northwest. Sometimes a little more north, sometimes a little more west. I'll focus on that a little bit later. In the summertime, we generally have smaller waves and a southern component to those waves at times. So going back to the 2016 wildfire season, the Severanis wildfire burned, again, much of the upper watershed. And one of the things that happens after wildfires like this is there's a multi-agency inventory of the wildfire, and they look at burn intensity and the potential for hazards that in those watersheds. And so there are crews doing these analyses right now for the wildfires we've had. And they're commonly packaged in what are called the BAER reports, BAER, if you're interested in this type of thing. And those are published as soon as they can. And they provide information such as this. This shows the probability for debris flows to occur in sort of the burned regions. And basically, the warmer the colors, the more likely that debris flows would occur, given if the pending winter was sort of an average winter. Now, a debris flow, what that is it's sort of a massive erosion event that introduces mud and rock and big boulders into channels, and that material is carried like as a slurry, and it's a very dangerous situation. And so, the incidence of those events is related to the how soil properties are changed following wildfires, and that's a whole nother topic that we could get into if you're interested. But in general, I want to just point out that the Big Sur watershed up here in the upper watershed, much of that is sort of in this high likelihood of having debris flow. So the potential for a lot of erosion after this wildfire was great, is sort of the take home for this. And what happened was that next winter was one of the wettest winters that has occurred in this region in our records. In fact, in the 50 years that the USGS has been collecting river discharge information here on the Big Sur River, the second highest peak occurred in that 50-year record in January of 2017. And so these are photos that were taken after some of those high flows, and you can see if you're a geomorphologist, you'd see, oh my gosh, there's all kinds of new sediment on the bed. You can see that, you know, material has been deposited all around these trees. The channel actually has changed quite a lot of. So when I see these photos, I think, wow, a lot of material has just kind of come through this watershed, and makes us ask, well, what happened at the coast to that? So to answer that question, what we're going to do is utilize the CoastSat database. And I showed some CoastSat data previously. If you're interested in CoastSat, I direct you towards, you just Google CoastSat, and Killian Voss, one of the co-authors, has developed this database from a bunch of analyses. Now he has posted data for Australia and all of California. But he's also worked up much of the Pacific Rim. That data will be coming soon. And so if you're interested in sort of broader scale Pacific Rim, there's a tremendous database about to be released. So what is CoastSat? Well, Killian came up with this neat technique of combining a whole bunch of tools to figure out where the shoreline is, or the best approximation for the shoreline is in satellite imagery. And it uses a combination here, I'm showing, you know, of machine learning, of this multi-band water index, and this Otsu threshold method, and then you use some tidal corrections, etc. And generally what happens, and this is using fairly coarse scaled imagery, Landsat and Sentinel-2 imagery, which is either sharpened or downsampled. And then you use this water index, and this is very similar if you've done some remote sensing to a lot of folks use an NDVI, a normalized difference vegetation index, to look at vegetation regions. Very similar type of index, but it's using shortwave infrared radiation rather than the near infrared, which is in the NDVI. And then you included in that is a classified image. And basically the idea is that the typical water index threshold, this is showing, this image up here on the right shows the water index. You can see here that water and land are defined really well by an index like this. But actually putting the line down the shoreline is kind of tricky. And it's actually easier if you classify the image into not just water and land classes, but also into white water and sandy beach classes. And that's basically what the technique does. It fits this threshold through a classified image, or a series of classified images. And then once those points are defined in the satellite image, you can sort of connect the dots and draw the shoreline using this marching squares technique. If you're interested in that, Killian has published this in Coastal Engineering. One of the things that is done, and I'll be showing you a lot of then, is you have these shorelines, but you can then extract them on cross-shore transects. And so if you look at a place and look, you know, where is the beach at this place over time, the nice thing is then you can correct that observation for tides. You could also correct it for waves and some other things. Those are not included in this analysis, but the data that I'll show here are tidal corrected. And in general, this does reasonably well. This just shows some data from Australia. RMC is something like 8 meters. And it works similarly across the different satellite platforms. You can see there with the box plots, you know, that they get gets a little bit better as the resolution of these sensors has improved with time. But in general, you're looking at sort of in an image, you know, one image, you're looking at, you know, an accuracy of about 10 meters or so. But that's good enough to see lots of interesting things like rotation of beaches shown here on the left. And this compares like imagery with real data, real surveying data shown here in the dark black line. And you can see that the black line and the gray areas line up really well. And that's because they're actually, the satellite tools working well enough to see this rotation in the beach. You can also see things like this is a big nourishment project at Duck in North Carolina. And the satellite can see that expansion of the beach. It's somewhat delayed because there weren't as many imagery available during the event, but you can see it's measuring sort of the extent of that new contribution of sediment from a nourishment project. So this works reasonably well. It certainly has some limitations, but it's a neat tool, and we thought let's try to see if it would work for the Big Sur River mouth. And really quickly, one of the reasons we decided to go the Big Sur River is because, gosh, it's a really small system. The beach is pretty dang narrow, but if it could work there, maybe it could work, elsewhere, and we could expand its use in the region, in the state. And so if you look at this year, the 2016-17 year, I'm showing just a couple of the images that are available. Here you see the raw image. This is the classified image with whitewater and sand and open water classified. And this is that water index showing just its raw value with a shoreline painted over it. And what you can see here is before sort of early February and before, we had a fairly narrow beach. There's this big plume of water coming out of the river in February. And then shortly thereafter, we see this big expansion of the beach and this interesting little area here. And then with time, and again, I'm not showing all the imagery, you can see how that broader beach seems to expand southward with time. And so, an area that was really narrow and probably very little sand now seems to have quite a bit of sand during the summer following those high flows. And so I talked about earlier, we can actually extract these data on Transects. And so here we're showing the Transects that we're using, and these are just spaced every 100 meters along this coast. So every 100 meters we have we look at the shoreline time series and derive something like this. And so here I'm showing this is the discharge record up here on the top, but then this shows, each of these panels shows another transect. So I'm not showing every transect, all 18, I'm just showing a unlimited set of them. And I'm showing also here the raw data in sort of the light blue, and then this low pass, it's a scatter smoothing function through the data, which it's sort of showing more of a seasonal event to seasonality filtering of that data with a gray line there. And there's this is really cool. I mean, one of the neat things is you get over 1,000 measurements of the shoreline between 1984 and the present. And so if you focus in on sort of the number of years before and after this this fire flood event, a couple things become apparent. The first is that, of course, the fire occurred in the summertime of 2016, but we didn't see this popping out of the beach. So going up is widening of the beach. We didn't see this widening of the beach until the river really discharged. So it wasn't until the winter that we saw that. So of course it was the hydrologic event after the fire that brought that sediment to the coast. And you can see as you go down the coast here how different this pattern looks. And so let's look at that a little more in detail. So one of the sort of simple things you could do is just say, okay, let's look at when this event occurred, about February or March or so. If you look at the 4 years before and the 4 years after that event, how different was the mean position of the beach? And I showed the mean and standard deviation with these pink boxes on each of those panels. So you can see sort of the before and after. And this is the difference in those. And you can see that after the event, the beach was wider by 20 to almost 40 meters. Again, that's 4 years before versus 4 years after. All those mean differences are highly significant using the Welch t-tests. So that's kind of cool. Another thing that's really interesting is I remember I talked about those rocky areas previously, and there I've kind of highlighted them here and shown them with gray bars across here. And what's interesting is the beach expanded less in those rocky areas than between them. In other words, the beaches sort of filled those cuspate forms between those little rocky areas. And that's kind of cool. Well, that's one thing you could do with these data. Another thing you could do is look at sort of when did that new sediment come, or when did you initially start seeing that that sedimentation cycle, that progradation of the beach. And there's a number of ways you can look at this. We came up with something fairly simple where we said, okay, let's think about the low point and the high point, before and after that addition of sediment, again, for the 4 years before and 4 years after. And we chose to do that using this low pass data. And then we found the date at which, half of that distance had occurred. In other words, at what date does the does sort of half of that progradation occur? And those dates are shown with those red dots. And I can't see oh, there's my cursor. You can see these red dots show that here. And what's interesting is you sort of go down the beach as you go further and further away from the river mouth. You can see that dot sort of gets later and later in time, and that's shown here in this graph, showing that near the river mouth it was fairly early in March or so, and then you had this region between sort of the rocky areas where it all came up at sort of about at the same time, sort of early summer. And then it almost took a year for sort of that and it's subtle here, I know, but for that sediment to sort of be seen if you do an analysis like this. So that's kind of interesting. And that means, on average, that's about 5 meters per day if you took an average. And obviously it didn't occur. It was a really neat stepping process. And the stepping is probably related to some of the seasonality you see in these data, some of these seasonal cycles. And of course, that's something you can look at too. And so let's quickly look at that. So one of the things you can do with these data, because again, we have data now from Landsat that goes all the way back to 1984. And then of course, we have multiple platforms in the air now collecting. You can look then at what is the seasonal cycle of these beaches. And so this is something we did by just taking all that raw data and detrending it using a similar LOES function, but it only removes sort of the annual to multi-year scales of variability. And then you can do a couple things with that. We actually fit a sine function through that. And we also looked at sort of monthly median values and looked at how much different they were across a year or across the calendar year. And so those results are shown here. And what's interesting is that you can see these annual cycles, the seasonality in the data here in the middle. Well, that comes out in these, this is the seasonal offsets, or how much the beach on average sort of is wider and then narrower. And what's interesting is here in the center of our study area, it's widest in the summer. So it's widest sort of later in the year. We have these big, broader beaches by almost 40 meters broader in the summertime, sort of classic sort of California beach cycle. And then on the southern end, we have a more subtle, you can actually see some of the seasonality to it, a more subtle signal, but it's actually broader in the winter, which is really kind of interesting and counterintuitive. It's not the classic model for beaches in California. It's kind of interesting to think about why that is. Is it related to south swell or other things? I won't touch upon that, but just to show that in general, we have a much greater seasonal cycle here in the middle of our beach, sort of between these rocky areas, than either in the south and especially up by the river mouth. You can see much dampened up there. Another thing you can do with these type of data is you can consider the longer interval of time, so the complete record from 84 to the present. And what's neat about these data is that they show some of those multi-year trends and patterns. And so here I'm showing just a few of those transects. Here, one near the river mouth, and then 3 more down the beach, and just showing sort of annual statistics. And I've computed these statistics on the water year, which is the October 1st through September 30th, to be consistent with the hydrologic records, but also because the winter time is the time where, we see usually the most change. I didn't want to cut that in half with a sort of arbitrary calendar year divide at January 1. But anyway, one of the interesting things to me, at least in these type of data, is that the beach was widest right after that fire and flood event in 2016-17. And so, for example, at this transect up at 300 meters, you can see this median position during that year was way seaward of anything that was seen in the decades before it. It receded quickly, and became narrow again, though. That's kind of interesting. On the southern end, if you look down at these transects, note that first year, really no change, not much different. But then over the years, it crept up and got broader and broader over time. And by the end, we see sort of the broadest beach that was measured. It's very similar to what was seen sort of in the early to mid-late 80s. But certainly the broadest beach it's seen in decades in that region, which is significant. So another thing you can do with these annual shorelines is you can start looking at comparing year to year and thinking about what happened at this beach and how did it evolve over time. And so here I'm just showing sort of the annual positions, and these are again for each transect. So we're looking at from the river mouth down to that small headland, and this shows how much beach change occurred between 2016 and 2017. And you can see that it broadened mostly in the northern region, almost 50 meters in some places, sort of 20 to 40, almost 50 meters of broadening here in the north, not much in the south. So what happened after that? Well, interestingly, a lot of that sediment was removed from the north, and we see a broadening in the south, almost like a shifting of that sediment from the north to the south over the following year. In the coming 2 years, sort of less happened. And it's kind of interesting because, between 2018 and 19, we see sort of a subtle erosion pattern. And then from 2019 to 2020, we see a little more of what we might think of as a beach rotation, where a beach erodes on one end and accretes on the other end. And what's really interesting, and I'll get at this in a second, is that those seem to be related to the waves that occurred during that winter. The waves in this winter were a little more directly from the west and larger versus more northerly waves and smaller. And I'll talk about these more in a second. I won't define these quite yet, but we'll get back to this in just a second. But overall, what's really neat is that when we started with a situation where the beach up by the river mouth was very broad during that first winter and the following summer. Again, 20, 30, 40, 50 meters broader than it had been. And then by the time we get to 2020, the beach is almost back to where it was originally in the north, but sort of almost a similar scale of broadening in the southern portion of our study area. And again, these rocky areas saw less accretion, less progradation. There's more sort of filling in between those rocky areas, which is kind of neat. Okay, so one of the things that we can do, and I sort of was alluding to this, is we can then take these measurements and use regression to just try to find if any of these variables, external variables, might have influenced these beach positions. And so what I'm showing here is our best estimated record of sediment discharge, annual sediment discharge from the Big Sur River. And Amy East helped a lot on thinking through how to do this. And I don't have time to talk about it. If you're interested, I'd love to tell you more about it. But in general, you can see this. Here's that big year that from the fire flood event of 2016-17. And so one of the things is, we can ask is, well, will regression, can it tell us anything about whether these beach positions are related to those sediment inputs? And so we did that, and here I'm showing again sort of along the beach for each transect. These are just simple correlation coefficients, R's, between sediment discharge and beach position, both for the same year, shown here in dark blue. So you see it's sort of well correlated here and near the river mouth, and then poorly and somewhat negatively correlated in the southern area of the beach for sediment input on the same year. For a 1-year delay, in other words, sediment input on this year influences the beach position, not in the same year, but in the next year, is shown in the light sort of brown color, showing that much more, there's a positive relationship in the southern region. These are fairly low though. And if you look at the sort of the scatter plots, they look like this. And so you can see sort of on the north during the same year, here's that, reasonable correlation. It's not just built on that one big event, but you can see it's, somewhat reasonable to see that that pattern in the rest of the data. If you look down on the south here, during that same year, there really is nothing much in there. There's a fairly weak relationship between what happened the year prior and what happened in terms of sediment discharge and the beach here. And so there's that 1-year lag effect. You can do similar things with waves. You can look at wave records, and here this is the a normalized winter wave energy flux, which is basically you look at the waves in the wintertime, and you compute the wave energy flux, which is sort of a function of the significant wave height squared and the wave period, and then you normalize it. So 1 is sort of an average winter, and greater than 1 is a big wave winter, and less than 1 is a smaller wave winter. And you can see some of our big wave winners like 98, and here's 83, etc. And then this is the direction of those largest waves, the upper 5% of the waves in the winter. And you can see here that usually the big waves come a little more from the west, but not always. And what's really cool about this is, again, these regression coefficients are kind of weak, but there's this interesting pattern in the north region is different from the southern region, and that these are inversely related. The wave energy flux and the direction of waves are sort of are inversely related. And let me just show you some scatter plots to help describe this. And we'll look at so again, on the northern region shown here in the blue in the top, and the southern down here. And what's interesting to me about these data, if you think about direction first, is that so as wave direction becomes steeper and steeper, greater and greater, more and more from the north, the beach in the north in general is a little bit narrower. It's not a great relationship, but it's subtle. But on the southern end, the beaches in general and the waves are more northerly, coming from the north. It's wider. In other words, the beach seems to rotate a bit as the waves become more and more northern. The beach rotates in relationship to that, and that's sort of a common thing that's seen in many beaches around the world. I won't, for time's sake, I won't touch the wave power. Again, they're somewhat weak, but there's some interesting patterns in that. I've said many times that these are fairly weak, but one of the things that you may be thinking is, well, gosh, you could probably just combine a lot of these variables and see whether they contribute together to explain more variance. And that's exactly what we did. This is sort of a very simple approach by doing stepwise multiple regression, sort of to combine those factors. We've added one more, and that is the position of the beach during the previous year. And so the results of the multiple regression are shown here, and this is now an R squared value. And so you can see that these are explaining roughly half, most of the times more than half, but roughly half of the variance in the data. And what's really kind of cool to me, and let me point out that these are shown, the most significant variable is shown first, and the length of it is the amount of variance of that first variable, and then the second most important variable is shown by its color. And the other thing is that we only include variables if they're significant at 0.05 level. And so what's kind of interesting to me is that we have sort of two different areas. And this area in the north, where the river sediment from the same year seems to control the beach position. But down here and south of that first rocky area, it's much more complicated. It's actually really interesting to think about that this area. There's a lot of what I think of as memory, or in other words, where the beach was yet last year influences where it is this year, and of course wave direction. You can see wave direction is sort of teal color, and a lagged response to river sediment. So there's this interesting pattern of things get more complicated in a sense as you move further away from the river mouth, but it's related to how much sediment was already there, what the waves were, and whether there was sediment discharge in the previous year, etc. So that can be sort of all distilled into this somewhat simple conceptual model. And hopefully this is a good way to distill it for you if that got a little bit confusing or a little too much in the weeds. And so in general, we have this situation here with shown in the top, where we have fairly narrow beaches. We have this seasonality to these beaches, et cetera. And we have these general wave patterns that I was talking about. When we have a big input of new sand, probably sand and gravel to this beach, you can see that mostly near the river mouth, and sort of within weeks to months that material is spreading to the south. And sort of during that next 1 to 2 years, we see that continuing to spread to the south and then really sort of filling up this beach. We probably start seeing loss around the headland, but we know that is many years to decadal in scale in terms of loss of material, because it's just been residing for so long. And then we have different wave conditions that influence the beach over time. We can have more direct waves, and we see the beach rotate in a certain direction, and then steeper waves, and it rotates in the other direction. You may be asking, how does this beach compare with other beaches in the Big Sur region which don't have sediment inputs? And I can tell you it differs greatly. And I don't have any time to show you this. If you're interested in this, I can definitely show it one-on-one or at another time. But I'm going to skip through all these plots. But just to show that here's a time series, the raw time series of the Big Sur River mouthy region, and just note how very different it is from the Point Sur beach. And when this expands up after that fire flood event, this one had nothing really to talk about. And I won't talk about these plots, I apologize, but just to say the Big Sur River mouth is very different because it has this active supply, and that's a really cool thing to me. Okay, so a couple quick follow-ups and then I'll be done. The first one is that I think it's, we picked Big Sur because it had these narrow beaches. And I'll be honest, I didn't think that we'd get much out of these data. And I was completely blown away that we could actually do the analyses we did and come up with results. And so what I think that shows is that we have some fairly useful tools to go back into the 80s for many of our beaches and try to understand their morphodynamics, how they've been changing over time. And so this is something, again, if there are students out there thinking about projects and they're interested in shorelines, coasts, et cetera, there's a wealth of information that is available to you from these satellites. And if you're interested in that, there are theses out there for you to work on. And so I would love to help you think about that if you're interested. But there's a sort of we do have a new tool in our toolbox, and I would encourage you to look into this if this is something you're interested in. Another thing that I want to point out is just going back sort of towards the data and say that not all wildfires are the same. And this is prevalent when you think of the basin complex fire, which actually burned more of the Big Sur watershed. Almost 90% of the watershed was burned back in 2008. But it had a much more muted, if not, negligible effect on shorelines versus the Soberanis fire, which was actually smaller but had so much more sediment discharge because of that post-wildfire rainfall. And again, It's sort of something to remember that wildfires are important, but you really need that rainfall afterward to generate the erosion and carry that sediment to the coast. So not all wildfires are the same. But that, you may ask, what about this one, John? Back in 77, we had the Marble Cone wildfire, which was followed by a really wet winter, and you're estimating a lot of sediment discharge. Unfortunately, we don't have Landsat imagery. We do have the California Coastal Record Project imagery, and unfortunately, they're not they do not have adequate overlap to do SFM photogrammetry. But you can see, it's a weak data point, but you can see a wider beach the year following, or a year and a half following that wildfire, which may suggest additional input. One more follow-up, and that is some of the narrowest beaches, or the beach was narrowest, I should say, especially near the river mouth during this recent drought we had. And so another thing to think about is that drought may have, the lack of supply during drought may have an important influence on the amount of sand and on beaches, especially those near river mouth. And you can see again here how narrow those beaches were during the drought, especially near the river mouth. I think it's important to point that out. Okay, so what we would love to do with this is do this on other beaches and start generating information to come up with a better understanding for how our beaches will respond to climate change. And so if you take the information that I've talked about here, a couple things I'll point out. One is that it's interesting to me, at least, how different our beaches are. And proximity to sediment supplies seems to be a very important variable in terms of how that beach may vary with time. Another interesting thing to think about is sort of the timing of fire and floods and drought. And if we're looking forward into the future, we're expecting prolonged droughts, but also increased wildfire, and when we get rain, more intense rain. And so that's, to me, may suggest that we would see a much more variable supply of sediment in time, and therefore maybe much more variable beaches over time. Fairly narrow, those near rivers would be fairly narrow during droughts and much broader during some of these fire flood events. Interesting to think about. It's certainly the sort of the next big question to tackle. So with that, I want to again point out my co-authors. Killian over here in Australia pulled together all the data from Landsat and Sentinel. Check out his papers. Fantastic work he's been doing. Amy East is an incredible geomorphologist and has helped me a ton with understanding the fire flood processes and thinking about sediment loads. And Sean Vatusek is this fantastic coastal modeler and has thought a lot about coastal morphodynamics and has helped me a lot with that and helped a lot in the analyses and thinking about how to analyze the data. So wanted to point out them. Thank you for your time. I am available for questions and discussion if you are. So thanks.
Good. Thank you, Jonathan. And we have some time available for questions here. So again, you have the raise hand feature under the reactions tab, or you can also monitor the chat if you have any questions.
I cannot see the chat, so I can't see what's going on there.
Yeah, I'll call on people, and okay. We have one question from Fuller, and yeah, feel free to show your video while you're asking a question if you want to.
Thank you for the great talk. I just wanted to quickly ask, it seems like with satellite imagery being so readily available over the coastline, this is a really easy way to scale the project back and look at larger areas. But could you foresee using technologies like drones with real-time kinetics to look at the centimeter changes within beach over the course of the year, and especially during these precipitation events?
Absolutely, fantastic question. And I can't see the video, so I couldn't see your face. But yes, absolutely. One way I think of the satellite analyses is they're sort of like the butter knife. You wouldn't bring them into surgery, right? It's providing it. The real strength is that there's so many measurements over such a long interval of time. But going to SFM from drone or airplane or handheld and or LiDAR is essential, absolutely, especially because one of the things that I wasn't able to do with these data, and we still aren't able to do, is to get elevation. And so we can look at Killian, this picture here of Killian. We might be able to map sort of where this line in the on the beach is, but we're not able to sort of fill out that volume window. And one of the things that I didn't talk about at all was a sediment budget for this beach. How much volume came into the beach, and tracking that volume over time. We track the beach position, and that's a big limitation of these technologies. And that's where the drone and other styles of surveying to get elevation are really essential. And so combining this with those types of measurements would be a great next step. Absolutely, great question.
And this is maybe a related question, but do you have any idea where that sand ends up? Does it end up nourishing beaches downstream after a few years, or does it just end up, getting swept off the really narrow shelf there?
Yeah, that's a great question. So there are a few more beaches to the south, and we don't see the effects from the river on those southern beaches. And so it may be by, when you go 10, 20 kilometers down this Big Sur coast, that it's just so, you lose that signal. It's just so smoothed out, right? You have all these little rocky points, and that the sand is moving through, that you just basically smear out that wave, in a sense. So I'm assuming it continues down south for a while, but then and then we sort of lose sandy beaches for a long stretch of the coast. So I'm assuming it's sort of there's another like 10 or 20 kilometers that it supplies, and then we may lose it. But it's a good question. We do have some satellite measurements I didn't show today of those down coast beaches, and we just don't see these hydrologic signals in them anymore. They look like Point Sur Beach, which is almost entirely dominated by waves. You see all the sort of classic seasonality to it. You see the big wave winners, it recedes much more than the smaller waves winners, etc. So you sort of get to a classic wave dominated shoreline.
All right, thank you. I don't see any other questions, and it's about 5 o'clock. So Jonathan said he's happy to stay afterwards if anybody wants to chat one-on-one or has any additional questions. But thank you very much, and we'll end it there.
Perfect. Thanks so much for coming.